give it like another 30 seconds before we go ahead and get started. All right, so this is 10 questions. So it is not too crazy, hopefully. So we have question 1, where you have a substituted product that has a different carbon skeletal structure than your reactant. And it's asking what mechanism had to have taken place here. All right, so we have a pretty broad diversity of answers. Does anybody want to argue for their answer choice? Yeah.
So this is substituted, either SCCS substitution, and then if it's like changing the skeletal structure, I think it's
Yeah, that was absolutely perfect. So just to kind of go over that again, based on the information that we see here, we see that we have a substituted product. So that will get rid of E1 and E2 as possibilities because we want substitution. And then the fact that we have this different carbon skeletal structure, anytime we have a different carbon skeletal structure, we're going to have a carbocation rearrangement. And we will go over, I have 2 problems that talk about carbocation rearrangements that we're going to go over later in class today. So hopefully, I know a lot of people express confusion on those. So hopefully going through the mechanisms a little bit slower will help on that. But generally, how do we feel about this? Does that make sense? Can you hear one more time? Yeah, perfect. So if we think about having a carbocation rearrangement, this means that it can be E1 or SN1, but the fact that it's substituted, that is why it can only be SN1. Okay. Okay, well, let us continue then. We will continue on. All right, okay. So question 2. Using a stronger nucleophile / base increase the rate of my reaction. What mechanism had to have taken place? All right, okay. So we're saying SN2 versus E2. Does anybody want to go into more detail on that? Yeah.
because I just know that the nucleophile doesn't affect the rate of SN1, so that one is the yellow and green. And then it says stronger nucleophile versus SN2 will affect the rate, and it possibly the stronger base will affect E2.
Yeah, definitely. We can summarize overall everything you just said there by looking at the rate laws. So the rate law for E1 is rate is equal to K times the concentration of electrophile leaving group. For SN1, we have, again, rate is equal to K times the concentration of electrophile leaving group. And then for E2, we have rate is equal to K times the concentration of electrophile leaving group times the concentration of base. And then for SN2, we have the same thing, except we have nucleophile as opposed to base. So electrophile leaving group times the concentration of nucleophile. So what happens is with these rate laws, we see that the rate of E1 and SN1 only depends on the electrophile. That's because when we're talking about the rate determining step, the first step, the only species that reacts is that electrophile. Whereas with E2 and SN2, these are concerted. They take place in a single step. So both species react at the same time. So the rate will depend on both species because that one single step is the rate determining step. Now, does anybody have any questions on that? Nah? All right. We will continue on then on this lovely journey that we're going on together. Okay, question 3. I add LDA and bromomethane to my reaction mixture. What happens? All right, so you guys are big fans of E2 here, which makes sense because how would we classify LDA? In terms of its nucleophilicity and basicity, what is it? Oh, what kind of base? It is a strong base. Specifically, it's a strong bulky base. And then what kind of nucleophile is it? It's a bad nucleophile, yes. So almost always when we see LDA, we see E2 happening. Why doesn't E2 happen here? And this is the structure of bromomethane, in case anybody wanted to see it. Yeah, Rachel? Yes, so if we go back to those tables, I'm going to flip back over here real quick. We see that when we have a bulky nucleophile in a strong base, then if we have a methyl alpha carbon, it will be SN2. Now this is tricky because it's kind of an oddity from what you're used to seeing. So that's really why I wanted to go over this here, just to make sure that this is something that you guys are thinking about. Does anybody have any follow-up questions on that? No? Okay. All right, we're mixing things up a little bit. Okay, question 4. How would you classify the molecule HSR? So overall, we agree on this. Sulfur as a whole is a nucleophilic atom, so it likes to act as a nucleophile. So if we have neutral sulfur or negatively charged sulfur, these are both good nucleophiles and weak bases. And this is one of those things that is again in those tables. So we can go ahead on. Oh, all right, to our next problem, problem 5. I add OH minus and a secondary electrophile to my reaction mixture. What happens? All right, okay. So we have E2 here. Does anybody want to argue that? Anybody want to support that with some evidence of any sort? Yeah?
I chose E2 because I knew OH was a strong base. So that's with the chart.
Yeah, so so OH minus is definitely a strong base, but we do have to be careful because it's also a strong So, but if we do go back and look at those charts, we see that if we have a good nucleophile and a good base, which is this row right here, and we have a secondary electrophile, we will have, that's really weird, isn't it? It's a weird noise. We will have E2 taking place here. So this mechanism will be E2. All right, okay. So the next, question 6. Which of the following is not true about SN2? Good. So we overall had a pretty general consensus. We know that that last one is wrong because SN2 is only one step. So if it's only a single step, then you don't have a second step. So that single step has to be the rate determining step. Now, if we think a little bit more thoroughly, why is SN2 stereospecific? What does it mean to be stereospecific? Yeah? Yes, beautiful. So if you're stereospecific, we can kind of break this word up because sometimes science makes sense like that. We are going to produce a specific stereoisomer. So we know that SN2 has an inversion of stereochemistry, so we have that stereospecificity. What does it mean to be concerted? Yeah, Rachel? Yes. So we know SN2 happens in a single step, so it is concerted. And then last step we have exothermic. Now, what does the fact that SN2 is exothermic tell you about the transition state? Yes, so we know it's going to be an early transition state. We know based off of Hammond's postulate that if a reaction is exothermic, the transition state will look more similarly to the reactant, so it's an early transition state. Kind of the way that I like to rationalize this, because memorization really isn't fun, is the fact that we know that the transition state is very, very unstable, right? So whatever looks more like the transition state is going to define if it's like an early or late transition state. So with an exothermic reaction, we know the reactants are less stable. So the reactants will look more similarly to the transition state, which is why you have that early transition state. Does anybody have any additional clarifying questions on this? No? All right, okay. So then let us continue. Okay, so then question 7. You guys are surviving. Which of the following correctly describes nucleophilicity? All right, so overall we agree. Let's kind of work through these though. First off, all the red choice, a more stable nucleophile is more nucleophilic. Why is that wrong? Yeah, so if you have a more stable nucleophile, then it's going to be relaxed. It's chill. It doesn't want to react. It just wants to like lay there and do nothing. You want your nucleophile to be angry. You want it to be upset. You want it to have an urge to attack. You want it to have a desire to attack. So as a result, you want to have a less stable nucleophile. To kind of go off of that, this idea that negatively charged nucleophiles aren't always best. Why is that wrong? Yeah? Yes, yes. So the whole idea of a nucleophile is you want it to have concentrated electron density. If you have a negative charge, you're going to have more of that concentrated electron density, so that is preferred. And then the last one, the bulkier a nucleophile is, the more nucleophilic it is. We know this is false because we want to have less bulky nucleophiles. Does anybody have any follow-up questions on that? No? All right, okay. Yeah. Yeah, of course. So we have two types of solvents. We have polar protic solvents. Oh, I have to turn on my pen, sorry. We have protic solvents, and we have aprotic solvents. Our protic solvents can hydrogen bond, whereas our aprotic solvents have no hydrogen bonding. So with our aprotic solvents, there's a slide at the end of your E2 notes that kind of list out those solvents. For your protic solvents, these are going to be alcohols for the purpose of this class. Okay. So, question 8. Which of the following forces stabilize carbocations and which is the most stabilizing? All right, good, good. So why does hyperconjugation stabilize carbocations? Yeah, Alex?
Because the electrons move around the
Yeah.
so that would like allow some electrons to flow to.
Perfect, perfect. So we know that hyperconjugation is when we have carbon-hydrogen sigma bonds align with our p orbital. And we're able to get some stabilization because yes, that carbon-hydrogen sigma bond will share some electron density with the p orbital. The same, well, not necessarily the exact same, but a very similar idea is true with resonance. But with resonance, we're actually able to push whole electrons into those p orbitals. Why does the inductive effect not stabilize carbocations? Yeah, so it's kind of based off of this idea that carbocations are electron deficient, so they want more electron density. The inductive effect pulls away electron density. So if we imagine having a carbocation like this versus a carbocation where that fluorine is just a methyl, what's going to happen is that fluorine is going to pull electron density away from our carbocation, thus destabilizing the carbocation. So the inductive effect always destabilizes carbocations. Anybody have any questions on that? Okay, cool. Can you say that one more time? Yeah, definitely. So if we want to talk about how resonance stabilizes carbocations, that's just based on the fact that if we have an adjacent pi bond, or adjacent p orbitals, we can go ahead and move these electrons right here and develop resonance contributors or resonance structures where that carbocation is not at that particular position. So basically, since we have this network of p orbitals here, that carbocation will be delocalized across those 3 orbitals. Does that answer your question? Cool. Does anybody else have any other questions in regards to this? All right, okay. So then we're going to continue. Oh, we're really mixing things up now. Okay, so question 9. Which of the following is not a polar aprotic solvent? So we touched on this a little already, but not entirely. Good, good. So there's kind of 2 ways that we can tackle this. The first way is that if you've already memorized those 6 aprotic solvents, you'll recognize that acetone, nitromethane, and this is HMPA, or hexamethyl phosphoric triamide, that those 3 are your polar aprotic solvents. So that's one way you can think about this. The other way is the fact that whenever we have an alcohol, it's going to end in this OL. So here we have decanol ending in OL. So you can have like methanol, ethanol, propanol, butanol, pentanol, hexanol, any of them. All of them end in OL. So that OL is always kind of your clue that that is an alcohol. Okay. We only have 1 question left. And then we will see who is the victor. All right, Madeline is now at the top. Okay, so question 10. All right, good. You guys got it right. That's good because all of the answers were correct. So I'm proud of you guys. That is great work. Okay, so what's going to happen at this point is I'm going to go ahead and stop sharing my screen. Okay, so we're going to go ahead and go over those 2 problems now. With these, you can listen if you want to. If you want to go over them with me, you can. If you're like, nah, I got this, I don't need to listen, then don't listen. You keep working on whatever you want to. That's totally cool. So with this first problem, this 8B, what are we thinking here? What mechanism is taking place? Does anybody have any ideas? We're saying E1. We have a vote for E1. Does anybody want to dispute that? No. Does anybody want to provide evidence for why it's E1? Yeah, so that's definitely one reason why. So if we think about HF, a lot of times when we have an acid in solution, it's going to be used to activate an alcohol, which means that eventually we're going to generate this F minus. And F minus is a weak base. Additionally, we know that this has to be either E1 or E2 because we form this alkene. So we can eliminate SN1 and SN2 based on the fact that there's an alkene. And then the fact that we have a weak base supports E1. Does anybody have another reason with why this would be E1? Another reason to support E1? Yep. Yes. So we also see a carbocation rearrangement here. So carbocation rearrangements, remember, tell you that it has to be either E1 or SN1. If we look at the structure of our reactants and products, I'm going to go ahead and number my carbons here. And I'm just arbitrarily numbering them. So that way it's easier to compare. You have a better side-by-side comparison. If we look at our starting material, this is a quaternary carbon. It has 2 methyl groups bound to it. So carbon 4 in the starting material has 2 methyl groups. But in the product, there's only 1 methyl group bound to carbon 4. So we lost a whole methyl group. Additionally, if we look at carbon 5, there's no methyl group on carbon 5 in the reactant. But if we go to the product, there's a methyl group right there. So there had to have been a carbocation rearrangement. How do we feel at this point? Does anybody have any questions when it comes to deciding that this was definitely E1? Okay, cool. So then let's talk about the mechanism here. And one of the reasons why I wanted to go over this problem is as a class, we haven't really done a problem where we have these boxes and we have to draw the intermediates. And that's important. So I want to make sure that we definitely do that before the exam. So does anybody have an idea with what the first step of this reaction would be? So you're saying the leaving group leaves, and I agree with you to a point. So the first step of E1 is that the leaving group leaves. But in this case, what is my leaving group? Yes, yes, perfect. So OH is my leaving group, and I know OH is my leaving group because F is still present. It's right there in our product. So you can't be the leaving group if you don't leave. So OH definitely has to be my leaving group. And OH is a bad leaving group. So since we have this acid in solution, we might as well help it out and make it a little bit better of a leaving group. So the first thing we're going to do is we're going to protonate that alcohol. We're going to protonate that alcohol, and we're going to generate a good leaving group. My oxygen is now going to be positively charged. And the only thing I'm changing is the protonation of that alcohol, so everything else is going to stay the same. So we're going to have this guy next. So what's going to happen next in my reaction? Yeah, now the leaving group is going to leave. And if you guys remember from, I don't know, a class period or two ago, we talked about how neutral leaving groups are the best leaving groups. And these are leaving groups that are neutral once they fall off. So water, that was supposed to be a 2, not a comma. So water, this boy N2, these are great, fantastic, phenomenal leaving groups. So we can go ahead and draw our structure once our leaving group leaves. Now we're going to have a carbocation at this position here. And we're going to see something like this. What happens next? Say it again, sorry. Yep, now we're going to have the rearrangement. So we're going to have our rearrangement next. And what we can see is we know that we want to add a methyl onto this carbon right here, this carbon I labeled 5 earlier. So I can choose either of these methyl groups. It doesn't matter which one. They're identical. And I'm going to draw an arrow. And I'm going to start my arrow at that bond and move it onto the carbocation. That was ugly, so we're going to do it again. We're just going to point it to the carbocation like that. And then I'm going to generate my new structure. So we're going to have a methyl here. This guy, that's the new methyl. That's the methyl I just added on. We have a methyl here. And what's going to happen is my carbocation is going to move because I'm adding a methyl group onto the old carbocation, which means that it's no longer going to be a carbocation because now it's going to have 4 bonds. But this other carbon lost a bond. It lost that methyl. So now it's going to be a carbocation because it only has 3 bonds. And then we're also going to have our fluorine. And I do want to note that it is important that I didn't draw the carbocation with any stereochemistry because carbocations are sp2 hybridized. So they're planar, they're flat, which means that there's not going to be any stereochemistry associated with it. So, do we feel good? Okay, and then we're going to have 2 steps, I guess, 2 more steps happen. What's going to happen next? Yeah, I mean?
So leftover fluorine attacks the carbocation.
So, if the leftover fluorine acts as a nucleophile and attacks the carbocation, will I form an alkene?
Oh, wait. No, sorry, I meant to say thank you. The fluorine deprotonates that beta carbon and then lone pairs from the hydrogen goes to the carbocation.
Perfect. So what beta carbon am I going to deprotonate?
The one that you did the rearrangement, also the one that has the name.
Yeah, so this one right here. And that's going to be because F minus is a small base. Small bases follow Zaytev's rule. And if I want to form the most stable alkene, I will have to deprotonate from this position here. Does that logic make sense to everyone? Okay, cool. So we can have either F minus or water. Either one of them will work just fine here. Come in and deprotonate the hydrogen and push those electrons to form an alkene right here. Oh, it's because I didn't draw this in the proper box. Sorry, guys. This structure right here, I was like, why does this not make any sense? And it's because I did something silly. So this structure right here is supposed to be here. So then we can draw that hydrogen. Coming in to deprotonate here, pushing the electrons here, and that will generate our product. So how do we feel about that? Anybody have any follow-up questions? Yeah.
I don't feel like every one reaction you don't have to actually alcohol. So like, is it everything that you want to add alcohol that you have to do it, or
So if you have an E1 reaction where your alcohol is the leading group, you will have to activate it to turn it into a Another kind of clue that you will activate in alcohol is that you have acidic conditions. So if you have a strong acid like HF, HCl, HI, any of those guys, you'll probably use that acid to activate alcohol. Okay, so then we are going to go over the next problem, which is a ring expansion. And just like with this next one, if you want to pay attention, if you think it's helpful, go ahead and listen in. If you don't want to pay attention, that's cool too. So let's talk about the mechanism happening here. What mechanism is taking place? SN1. Why do you say it's SN1? Perfect. So reason one why it's SN1 is that this is a substitution. And we know it's a substitution because there's no alkene. At this point, you only know 4 reactions. 2 of them form an alkene, 2 of them don't. So if they don't form an alkene, you know that it has to be either SN1 or SN2. The second reason why it's SN1 is because you have this ring expansion. You cannot have a ring expansion with SN2. You cannot have a ring expansion with E2 because they don't involve carbocations. You need a carbocation intermediate to have a ring expansion. So these 2 clues tell you that it has to be SN1. How do we feel about that? Now, ring expansions are the easiest carbocation rearrangement to recognize. Yeah, Rachel? Did you have a question? Oh, okay, sorry. You just were like very enthusiastic. Okay. So ring expansions are the easiest carbocation rearrangement to recognize because of the fact that the ring is changing in size. So anytime you have a ring getting bigger, you know it's a carbocation rearrangement. Now, that being said, just because they're the easiest to recognize doesn't necessarily mean that they're the easiest to understand. Now, let's go over this right here. We know it's SN1. What's going to be the first step? What do you guys think is the first thing that happens? The leaving group leaves, yes. Now, in our previous example, we had an additional step before our mechanism where we had to activate the leaving group. In this case, we don't have acidic conditions, and we also already have a good leaving group. So we don't need to activate a leaving group. So our leaving group is going to leave. And then one of the reasons why I really love drawing the arrow pushing is because it tells me exactly what is happening. I know sometimes when you're drawing a mechanism, it can get a little bit stressful and you're like, oh, what bonds do I have to change? What do I have to break? What do I have to do? And I can see from that arrow that I drew, the only thing that should be changing is my leaving group should leave. Everything else better stay the same. So going from here, I'm going to number my carbons. Numbering your carbons makes ring expansions a million times easier. So I numbered my carbons. Now what's going to happen with a ring expansion is I kind of think of it as you're opening a door. You're kind of swinging a door open. What's going to happen is we are going to take and we're going to break this bond right here. This bond right here between carbon 2 and carbon 5. And what's going to happen is we're going to form a new bond between carbon 5 and carbon 1. So if you look, it's kind of like you have this door that's swinging open, and you're allowing another carbon into your ring. Now, you could also look at this situation and have, let me renumber this real quick. So 5, 4, 3, 2, 2, 1. You could also view this as this bond right here breaking between carbon 3 and carbon 2. And that will give you the same exact product. So in case anybody was like, but why didn't you choose that bond? That will also work. It's the same exact idea. Basically, you want to break a bond that is adjacent to the carbocation. Yeah, I mean?
Is there an arrow pushing?
Yeah, definitely. And we're going to go over that arrow pushing. I just wanted to clarify that you could use that other bond as well, as long as it was a bond that was adjacent to the carbocation. But I am going to erase this structure right here, just because it's not as pretty as the red one. The red one's nice. Okay. So yeah, we're going to go over the arrow pushing, and I'm going to erase these dots right here, just because that was for me to show you where that new bond was forming. And it's not involved in the arrow pushing. The arrow is going to start at the bond that you're breaking, and you're just going to point it to the carbocation. So it's a pretty simple arrow. You're going to start at the bond breaking, and then you'll point it to the carbocation. And this is where it gets a little bit tricky when you're actually drawing that new ring. So I'm going to start out by drawing a cyclopentane ring, because I know that with a ring expansion mechanism, I add one additional carbon to my ring. So if I start out with a 4-carbon ring, I'm doing ring expansion, I need to end with a 5-carbon ring. So I know I'm going to have a cyclopentane ring. Now what I'm going to do next is I'm going to number my substituents. Now this one's a little bit easier because we only have, or I'm going to number my carbons, excuse me. This one's a little bit easier because we don't have as many substituents. But I'm going to go over it a little bit more detail just to make sure that everybody's on the same page. So I'm going to start out with carbon 4 and carbon 3. Looking at my initial intermediate structure, this guy right here, I see that the bond between carbon 4 and carbon 3 stays the same. There's no arrows. There's nothing's going on with it. Same with the bond between carbon 3 and carbon 2. There's no arrows. And the bond between carbon 2 and carbon 1. Additionally, the bond between carbon 4 and 5 also stays the same. My new bond is this bond right here between carbon 5 and carbon 1. So what I'm going to do next is I'm going to throw on my substituents. I know that I have this methyl over here that is bound to carbon 1. Oh, I don't want to do the highlighter there. Let's unhighlight that. I have my methyl right there. It's hanging out, doing its thing. But then I have to figure out where my carbocation is going to be. Now, if I think about my starting material, my reactive intermediate over here, I have this bond between carbon 5 and carbon 2. But if I look at my product, I am breaking the bond between carbon 5 and carbon 2. I broke that bond right there. So I'm taking a bond away from carbon 2. But I'm forming a bond between 5 and 1. So I'm taking a bond away from 2 and I'm giving it to 1, which means that my carbocation is now going to be on carbon 2. How do we feel about that? Good, good. Okay. So then I'm going to erase that dashed line. And then at this point right here, we could potentially think that maybe a hydride shift would happen, because we could have a hydride shift to form a more stable carbocation. But in this case, we know that a hydride shift is not going to happen because our nucleophile attaches to a secondary alpha carbon. So if you're not given the product, Axelson will say something along the lines of perform however many carbocation rearrangements occur or needed to occur to form like the most stable carbocation. Or she'll give you the product and then you'll base the number of carbocation rearrangements off of that product. Does that kind of make sense or does that not quite make sense? I'm getting nods. Okay. So then my last step is just going to be that my second to last step, excuse me, is going to be my nucleophile attacking. We're going to get this guy right here. And then I will have to have one additional acid base step where I can either have my water or bromine, either one can come in and deprotonate. How do we feel about that? Okay, hopefully that wasn't in such detail that it was excruciatingly painful. And hopefully that did help. If not, if it was painful, I'm sorry, but sometimes you have to experience pain in life, I guess. So does anybody have any additional questions on this? Okay, then I'm going to go ahead and stop sharing my screen here. I'm going to stop